A classic static equilibrium problem is a ladder against a wall. So you see over here on the right hand side, I've drawn a red wall. I've got a ladder leaning against it. And so because this is an extended object, we have to consider the fact that it can rotate. And so with static equilibrium, that both the net force and the net torque are equal to 0. So with net force equal to 0, it means that there is no change in the velocity of the ladder. And with net torque, there is no change in the rotational rate of the ladder. So if we think about what's happening with the ladder, we know that the weight of the ladder acts toward the center of the earth. We also know that because the bottom of the ladder is sitting on a surface, that there's a normal force with the floor. There's another surface here, that's the wall. So there is a normal force perpendicular to the wall. And then we've got some friction that is acting along the floor here. And we'll say force due to friction for the floor. That's static friction. There also then is some friction that's keeping the ladder from sliding down the wall. So we've got those forces essentially that are acting. And so the net force equals 0. So that tells us that the weight of the ladder is supported by the floor, normal force, and this friction with the wall. So we can actually write that out. And we would say mg is equal to friction with the wall plus normal with the floor. Now remember, friction with the wall is the coefficient of friction between the wall and the ladder. The normal force of the wall, that is by definition, so plus the normal force of the floor. So just doing a little bit of substitution so we can kind of see what things that we can use. Then we have in the horizontal direction, we have that this force due to friction here and the normal force of the wall have to be equal to one another. So we can write that the force due to friction with the floor is equal to the normal force that the wall supplies. And keep in mind that the friction with the floor is the coefficient of friction with the floor, normal force of the floor. So that's going to allow us to do some substitution in this case. Now we're going to introduce the idea of torque. And so with a net torque being applied, our angular acceleration is 0 here, so there is no net torque. That means the twisting action of each one of these forces is balanced. And so the forces that are causing clockwise rotation and the forces that would be causing counterclockwise rotation are equal to one another. In order then to solve for net torque, we need to pick an axis. So the first thing we'll do is assign an axis. We can pick any one we want to. A good one to pick here is this point here with the floor. The nice thing about that is then there are two forces for which the lever arm is 0, and so we only have to consider the torque for the other three forces. And so if I'm writing the net torque, that is the torque from the friction with the wall, the torque from the normal with the wall, and the torque from the weight. All right. So if you recall, torque is R cross F. And so we're going to be looking for the R value for each one of these and the force. Okay, so we want to think about how each force is causing torque on the ladder. So we're going to start keeping in mind down here is our axis, and we'll just take the forces one at a time from the top. So let's draw this one, which is the normal force that the wall exerts on the top of the ladder. And so if I draw the vector that represents the lever arm, I'm going to draw from the axis all the way out to the force, and that's going to be the lever arm for the wall. But keep in mind, when I'm looking at this, I only want the piece of this normal vector that's perpendicular to the lever. So I'm going to make a right triangle out of this. So I've made a right triangle where the normal to the wall is the hypotenuse. And if I mark down here, there's my angle. And so that means if I'm looking up top, that's this angle also. And so if I'm thinking about the piece that is perpendicular to the lever arm, it's just this piece of the normal. So that would be NW sine phi. So if I want to write the torque, then I would say the torque is equal to the force times the lever arm. And if I were to hold the axis down here and treat the ladder as a lever and push on it, it's going to try to rotate counterclockwise. So this is a positive torque. I have another force at the top. So the other force at the top is the friction that points up. So we've got some friction between the wall and the ladder. And so again, I want to think about how it's acting on the ladder. It's acting at the same distance as before, but if I make a right triangle where the hypotenuse is the force, and I think about what's happening here, here's phi, so this is going to be 90 minus phi, and so that makes this phi, and so for that force, the torque is the cosine component, so force of the wall cosine phi times the lever arm. And if I, again, think about my axis being down here at the bottom, push up on the end, that's going to also give me a counterclockwise rotation, so I can write the torque vector as plus. Third and final force is acting down, and so that would be the weight. I want to make a right triangle where the hypotenuse is the weight. And so I see that if this is phi, then this angle is 90 minus phi. And so this piece that's perpendicular is the sine component of the weight. Also notice though that I have a different lever arm here. My lever arm for this force only goes halfway because this is a uniformly distributed weight throughout the beam. So when I write this torque, it's going to be mg sine phi, except instead of the whole length, it's half the length of the whole ladder. Also, if I were to hold the axis down here and rotate that, it would go in the direction of the clock, so that makes it a negative. And so if I want the net torque, then I just sum all of these. And since this is not rotating, that whole sum equals 0. And I can see that there are some ways for me to solve now based on knowing these pieces. And so I see they all have some similar terms that I can work with, but this process will get me started on any static equilibrium problem. Summing the forces, summing the torque, so that then I can find out other things about the system.